Hello and welcome back to Part 11 of the Delaware Tech Physics 111 Exam 1 Preparation and Practice Exam covering motion, also known as kinematics. In this section, we're going to continue with vertical kinematics problems, specifically those problems involving the simple drop of an object from some tall height. So the problem says a steel ball is dropped from the top floor of a very tall building. No one is below. All right. Part A, what two given kinematic properties do you already know the value of? In other words, what do we already know? Hint, there are a total of 5 kinematic properties, okay? Remember those properties are your change in position, which is also known as displacement, your initial velocity, your final velocity, your acceleration, and your change in time. Which ones do we already know about? So I'll just make the list over here. We have displacement, we have initial velocity, we have final velocity, we have our acceleration, and we have our change in time. Well, we don't know anything about displacement because we're just told it's a very tall building. We have no idea how tall the building is, and we have no idea how far the object has fallen as it's falling from the top of this building. The initial velocity, well, we're dropping the ball. So that means we're starting from a velocity of 0. So our initial velocity is 0 meters per second. Anytime you have a drop where you're not imparting some initial velocity, you assume that initial velocity is 0. The final velocity, well, that's going to change with time. So we don't know that. The acceleration, well, this is a vertical drop. So the question is it a free fall acceleration, in which case the acceleration is g, or is it something else? Well, it's a steel ball. We're going to assume there's no significant air resistance, and therefore the acceleration will be g. And we know the value of g. It's negative 9.8 meters per second squared. Remember, any acceleration is going to be in meters per second squared. And the last parameter to consider would be the change in time, but we haven't been given any information about that yet, so that is not one of the two givens. So we have an initial velocity of 0 meters per second, and our acceleration, our downward acceleration of g, is negative 9.8 meters per second squared. These are the two things we know already. Part B, if you're also given a change in time, delta t, which kinematic equation should you use to calculate the final velocity? Well, which variables do we have information on? Well, we know the value of the initial velocity. We know our acceleration is now g, and we know what that value is. We're going to be given a delta t value, and we're being asked for the final velocity. So we need a formula that has all 4 of those and does not include displacement. And only one formula fits that, and that would be formula number 2, the one that states that the final velocity equals the initial velocity plus normally our acceleration, but in this case we can replace that with g, times the change in time. So there's our formula. Part C, using the specific given values that you recorded in Part A, how would you simplify the above equation for the final velocity? Well, we know the initial velocity is 0. So the initial velocity term will just be canceled. Just cross that out. And that leaves us with g times delta t, but we know g is equal to negative 9.8 meters per second squared. So we can rewrite this as the final velocity equals negative 9.8 meters per second squared times whatever our change in time is. Part D. Now Part D says use your modified formula, in other words, the simplified formula of final velocity equals minus 9.8 meters per second squared times the change in time. to calculate the final velocity at various times. And we're given times of 0 seconds, or 1 second, 3 seconds, 5 seconds, and 8 seconds. So we're going to have 5 separate calculations. We have our simplified formula of V final equals negative 9.8 meters per second squared times whatever our change in time is. Well, now that we have an equation, we just plug in 5 different times to get 5 different final velocities at those times. So our first final velocity, we can call it final velocity at time 0, would be equal to negative 9.8 meters per second squared times 0 seconds. Well, the seconds will cancel out one of the seconds in the denominator, and we'll be left with meters per second. But 0 times anything is going to be 0, and in this case, meters per second. So that'll be our velocity at time 0, which makes sense. The ball has not started dropping yet, so the initial velocity and the final velocity at time 0 are the same time at time 0. So that ball hasn't moved yet. So what happens at 1 second? Well, the final velocity after 1 second of falling is negative 9.8 meters per second squared times 1 second. Well, that works out to a velocity of negative 9.8 meters per second. You might say, why is it negative 9.8 meters per second? Well, it's falling downward. Remember, the velocity is vertically downward, so our velocity will have a negative value. The next time is 3 seconds. So our final velocity after 3 seconds of falling is just negative 9.8 meters per second squared times 3 seconds. Plug that into your calculator, and you'll get a value of negative 29.4, and again, it's meters per second. For 5 seconds, plug in 5 for that value. 5 seconds here, we plug that in, and we get a velocity of negative 49.0 meters per second. And of course, after 8 seconds of falling, multiply the negative 9.8 meters per second squared times 8 seconds, and we get a velocity of negative 78.4 meters per second. Now that you have all 5 values, record those in the table in part H. There's a column labeled final velocity, and there's another column marked displacement. These will be under the final velocity. Now, you'll notice these velocities, they're either 0 or negative values. If you were asked for a speed, you wouldn't need the negative value. You could just say 0 meters per second, 9.8 meters per second, 29.4, 49.0, and 78.4 meters per second, because speeds are always going to be positive value. Okay, let's look at the next page. Part E. If you only know the 2 givens you listed in Part A, remember those 2 givens where the initial velocity is 0 meters per second and the acceleration is g, which is negative 9.8 meters per second squared, as well as the change in time, delta t, which kinematic equation should you use to calculate the displacement? So before we were calculating final velocity, now we're calculating displacement. And the question also has a little note that says, assume you cannot trust the final velocity values that you just calculated in Part D. So don't include any equations that use final velocity to calculate the displacement. So considering our 5 parameters, our displacement, our initial velocity, our final velocity, our acceleration, which is g, and our change in time, delta t, we are asked to calculate displacement. We know our initial velocity is 0. We know that g is negative 9.8 meters per second squared, and we're going to be given a delta t or more than one delta t. The only thing we do not know is the final velocity, because we're going to assume that our values that we just calculated can't be used in this second equation. So which equation do we use that has those four variables in it? Well, the only equation that has those four variables alone in it is equation number 4, the equation that says that our displacement is equal to our initial velocity times our change in time plus 1/2 times our acceleration, which in this case is g, times time squared, our change in time squared. Well, part F says using the given values that we recorded in part A, remember initial velocity is 0, how would you simplify the above equation? Well, first of all, we have a term in there that has our initial velocity in it, and that term can just be crossed out. It's going to be equal to 0. And the remaining term is 1/2 g times delta t squared. Well, now we just replace the g with the value we know for g. So 1/2 times our g, which is negative 9.8 meters per second squared, times our change in time squared. We can simplify this further by just multiplying these two numbers together. We would get negative 4.9 meters per second squared, in other words, half of g, times our change in time squared. And that's a much more simplified version of the same equation. Okay, looking at part G, it says use your modified formula for final velocity in part F to calculate the displacement at various times, 0 seconds, 1 second, 3, 5, and 8 seconds. That is, there are 5 separate quick calculations. Please show your work here and place all your answers in the table in part H like we did before. All right, so now you're going to do the same thing you did in part D, solving for final velocity at 5 different times. Now you're solving for displacement after 5 different times of falling. So we're going to take our formula, delta y equals negative 4.9 meters per second squared, and that will be times whatever the amount of time is squared. So the displacement after 0 seconds, as you might expect, is going to be 0. Why? Because when we multiply negative 4.9 meters per second squared times 0 seconds, and we square that 0 seconds, we're going to end up with 0. Now, what are the units? Well, this is going to be seconds squared, so it will cancel both of the seconds in the denominator of the negative 4.9 meters per second squared. So the only unit we'll be left with is meters, as you would expect, because this is a displacement. And this makes sense because if you've only fallen for 0 seconds, that means you haven't fallen at all, so the displacement is 0 meters. At 1 second, we'll substitute in 1 second for the change in time. We have negative 4.9 meters per second squared. And now we're multiplying that by 1 second quantity squared. So that will be still 1, but it'll be seconds squared. We multiply that by negative 4.9, and we have a displacement of minus 4.9 meters. Why is it negative? Because the steel ball is falling downward. It's a downward displacement. After 3 seconds of falling, you multiply the negative 4.9, as always, meters per second squared, times 3 seconds, quantity squared. So this number will be 9 seconds squared. You multiply that by the negative 4.9, and you end up with the displacement of negative 44.1 meters. You'll notice the displacement increases tremendously with time. At 5 seconds, we find the displacement is again minus 4.9 meters per second squared. Now it's multiplied by 5 seconds quantity squared. So this number will be 25 seconds squared. And when we multiply that out, we get that the object has fallen 122.5 meters. In other words, the displacement is negative 122.5 meters. And finally, our displacement after 8 seconds is equal to negative 4.9 meters per second squared times 8 seconds quantity squared. So this part of the formula is going to be equal to 64 seconds squared. When you multiply that by negative 4.9 meters per second, you end up with a whopping negative 313.6 meters. This is a huge height. This is over 1,000 feet. So while you notice the velocity increases gradually with time, the displacement increases with the square of the time, so it is a much faster increase in displacement. And when you've completed all of these calculations, you're then just going to record them in this table here. And if you go to the very last page of the answer key, you will see that completed table here. And with this, we'll stop.